Okay, so now we will revisit this game. Before we do that, I should mention that we talked about weak sequential equilibria. We can have stronger notions of sequential equilibria, um, make the belief consistency stronger, right? So we could do that by having the restriction that the belief system has to be consistent with strategies even at information sets that aren't reached with positive probability. Um, but that's less useful. It doesn't actually take away equilibria that we want to take away. It doesn't reduce the set of non-plausible equilibria in the games that we'll consider. And so we won't be considering that refinement in our course. Okay, so let's look at this game. Let's start with the fact that EJG is a weak sequential equilibrium. Right? Player 1 plays E and J. Player 2 plays G under a belief that D is reached with 1/3 probability and C is reached with 2/3 probability if player 2 is within this information set. And because this belief is never contradicted, EJG remains a weak sequential equilibrium. On the other hand, DJG is not a weak sequential equilibrium because if you play DJG, then D is reached with a probability 1, and if D is reached with a probability 1, then for P2, playing F is optimal. So DJG cannot be a weak sequential equilibrium because either your beliefs will be wrong as player 2, or as player 2 your actions will be wrong if you're ending up playing G. Now, let's start from scratch, okay? Just have this as the game and try and find all the weak sequential equilibria of this game. The way we do it will be somewhat similar in spirit to what we did when we were trying to find all the subgame perfect equilibria of the game. We try and work backwards. So, over here, player 1 will obviously choose J, right? There's no uncertainty, right? If player 1 reaches this information node, 3 is better than 0, player 1 will choose J rather than K. Let's go one step up. When would player 1 choose E? Let's ask ourselves that question. Player 1 would choose E only if player 2 is choosing F less than 2/3 of the time. Let me write that out. E only if the probability that player 2 chooses F is less than 2/3. You could also have equal, because at that point player 1 will be indifferent. Does that make sense? Because if player 2 is choosing F 3/4 of the time, then player 1 would deviate profitably and choose C. Right? Because then it's C, F, and J, and player 1 gets 3 instead of 2. It's this 2 and 3 that give you the number 2 divided by 3, right? Because you can get 2 for sure as player 1 by playing E, but you could get 3 if you know that player 2 is going to play F. Okay. For player 2 to choose F less than equal to 2/3 of the time, either as player 2 you're choosing F some of the time, so either F is between 0 and 2/3, for that you would need a belief system that assigns a weight 1/2, 1/2 to C and D. Now as player 2, with your options of C and D, you only get positive payoff if either you end up here or you end up here. Right? Those positive payoffs are equal. You never actually end up here because player 1 always chooses J, so it's as if this game ends for you at 3-0 if you're player 2. So if you're player 2, you're indifferent between choosing F and G only if the weights on these two nodes, on reaching these 2 points, is 1/2, 1/2. Let's call this P Q and R. Okay. So only if P equals Q. So that's fine. Or alternatively, you could choose E if F is 0. If the probability of player 2 choosing F is equal to 0, then that means that player 2 is always choosing G, which simply requires Q to be greater than P or equal, right? Then you always choose G. So this simply requires any number greater than 1/2 here, or less than equal to 1/2 here. And so all of these will constitute weak sequentially rational equilibrium. Weak sequential equilibrium. Let's see. So any strategy of player 2 is optimal if player 2 believes that the history C happens with probability 1/2, and then you choose any F that's between 0 and 2/3. And player 1 always chooses EJ in this. So one set of sequential equilibria is where player 1's strategy is EJ and player 2's is like this. The probability of choosing F is between 0 and 2/3, and mu is such that you put a weight of 1/2 on C, 1/2 on D, or the probability of, or you just play G, where the probability of F is 0, and your belief system places the weight of at least 1/2 on D. And both of those are perfectly fine. Those sets are perfectly fine. And so basically what you found is an infinite number of potential equilibria because you're choosing F from a continuous distribution. In all of these games, however, the outcome is still just E because player 1 plays EJ. Let's also consider what happens so we know that playing EJ for player 1 works as a weak sequential equilibrium under these beliefs and strategies by player 2. Would there ever be an equilibrium in which player 1 chooses C and or D with positive probability? So let's suppose player 1 chooses C and or D with positive probability, right? And the probabilities are P and Q. Then the likelihood of this history having happened if player 2 reaches this intermediate node is going to be P divided by P plus Q. This will be Q divided by P plus Q. If for player 2 to play, if P is greater than Q or equal to Q, then player 2 can play F. If Q is greater than or equal to P, then player 2 can play G. If Q and P are equal, then player 2 can mix, right? So, when would player 1 play D, for instance? Player 1 would play D only if player 1 believes that player 2 will play G. Player 2 will play G only if Q is greater than or equal to P. Oh, sorry. Messed this up completely. You play G only if you think this is more likely. And so P greater than or equal to Q, Q greater. And you play F if you think this is more likely. So if player 1 plays D more often, then player 2 is always going to choose F. If player 1 plays C more often, then player 2 is always going to choose G. Right? Player 1, okay, let's say player 1 chooses Q greater than P. Right? If player 1 chooses Q greater than P, then player 2 will always choose F. and then player 1 will not want to choose Q, player 1 would rather choose R, choose to play E all the time, right? Because this is not worth it for player 1. If player 1 plays C more often, then player 2 will play G more often, and player 1 will want to deviate to playing either D or E. And so that doesn't work either. Let me read this out. Think of this backwards, okay? Think of now player 2's actions and what player 1 would do. I think it works out easier that way. If player 2 always plays G, then player 1's best response is to set Q equals 1. If player 2, in which case player 2 would want to switch to playing F rather than G, so that doesn't work as an equilibrium. If player 2 always plays F, then player 1 would always play C, and you'd end up here, and again player 1 is happy with that, but player 2 would want to switch, so that doesn't work as an equilibrium. So we can't have an equilibrium where player 2 plays G always, or where player 2 plays F always. So what if player 2 mixes? If player 2 ever mixes, so assigns positive probabilities to both F and G, then for that to be an equilibrium, player 1 would have to set P equals Q. Otherwise, player 2 would not want to mix between F and G. And if player 1 is setting P equal to Q, then player 1's expected payoffs, irrespective of what mix player 2 chooses, player 1's expected payoffs from assigning any positive probabilities to C or D will be lower than what player 1 would get by just choosing E all the time. And so we have no equilibrium in which C and D, or separately C or D, are played with positive probability. Sorry if this wasn't super clear. I tried explaining it a bunch of different ways. If this doesn't make sense, please ask me about this in one of our Zoom meetings.